Today we'll start a new topic. Our topic is the numerical integration and numerical differentiation. Let's first we will start the numerical differentiation. If the last classes up to last 4 or 5 classes, if you can recall the memories that we know interpolate how to interpolate the unknown values for a given function with the even and uneven interval of the arguments. And using those knowledge, we will start the numerical differentiation. Actually, in numerical differentiation, we will not nothing new, just the previous concepts, previous equations of Newton numerical interpolation, and by using those numerical differentiation. So first question may arise, so what is differentiation in calculus? In your intermediate level of study, everybody passed those the steps, the numerical normal differentiation. That means in common sense, this is nothing but dy by dx for derivative. Okay, the very simple answer is the derivative, dy by dx. This is the first differentiation. And second differentiation, the second or the second derivative, d square y by dx square, and go on. Third derivative, fourth derivative, up to in some cases we need d to the power 4 up to fourth derivative, and so on. The very simple thing is, if we have a function y is equal to f of x, that means uh, a function, this function can obtain for a certain number of set of value. That means xi yi, that means number of set of value. So for this number of set of value, we can easily put a equation. Okay, y is equal to f of x, such types of equation. So if we have a equation, then we can simply, what can we do, dy by dx. Okay, that means this will be ddx of f of x. That means if we take the derivative of this function, this is the dy by dx, and parallelly d square y by dx, this is nothing but f double prime x. That means if you have a function for a given set of value, that means in last few class we may discuss that in the numerical interpolation, we simply do a form a equation for a given set of value. Okay, simply put an equation or in the equation form, and thereafter, after forming the equation, we simply put the value of x for any values, for any intermediate values or anything. Any values of x will give you the corresponding y value. In numerical differentiation, the same procedure will be applicable as before for numerical interpolation, like that. In numerical interpolation, we at very first step we know the Gregory Newton forward interpolation formula, and thereafter backward interpolation formula and central interpolation formulas as well. Again, the same things will be arrived here. Forward interpolation formula, backward interpolation formula, central interpolation formula. So these are the basic three things, and in which basis we choose the forward, backward, and central. The concept is very simple. If you require data, x point is near to the starting point of the data set, then we use the forward interpolation formula. If it is very close to the end point of the data table, then we use the backward interpolation, and if it in the central region, we will use the central interpolation formulas. Okay, and based on this and another patterns we studied, that was for the Newton divided difference interpolation formula or the Lagrange interpolation formulas. Those are not equispaced x values. Okay, these are for the equal value h, equal steps, and if there is no equispaced x value for the function, we use two method. First one is the Newton divided difference, and another one is Lagrange Lagrange interpolation. So these are the two methods. So in each method the basic concept is same, y is equal to f of x. That means based on the given data set, either it is equispaced or not equispaced. Both cases we will form a function of x, y is equal to f of x. So the next task, numerical differentiation, is very simple. Just take the derivative, first derivative, second derivative. This is simply numerical differentiation. So again, for these types of problems you also need to form the uh, difference table. So difference table formation is as before, and is common for numerical differentiation as well. Let's start with the derivatives using Newton forward difference formula. Okay. Newton's forward difference formula. So if you can recall the forward difference formula, this formula was actually y is equal to y0 plus p del y p into p minus 1 2 factorial del square y0 p minus 1 p minus 2 3 factorial del cube y0 plus so on. So here p is equal to x minus x0. For forward difference, p is equal to x minus x0 divided by h. So look at this. In this equation, our target is to find dy by dx. For the first derivative, dy by dx. Second derivative, this will be d square y by dx square. So here we have a function y with respect to p. That means the variables are y and p is also linked with x. So differentiating, so we need to do dy by dp. Okay, first dy by dp. Okay, in this case dy by dp, and this is y0 is a constant term, constant value, so this will be 0 plus p del y. So this is p dy by dp will be 1. That means this will be del y0 plus if you break these terms in suitable form, that means p square minus p, derivatives will come 2p minus 1 divided by 2 factorial del square y0 plus this is 3 factorial, and these terms, these total terms after breaking you will find p cube minus 3p square plus 2p. So after deriving, this will be the first derivative of p, this will be 3p square minus 6p plus 2. Okay, and del cube. I see. So the fourth terms will be as well. You can simply need to break down the terms with respect to p in a simplified form and then take the derivative. So this is your the dy by dp. So now our target is to find dy by dx. So you know this as before, dy by dp. Sorry, this is nothing but dy by dp multiplied by dp by dx. Okay, this can be written. So dy by dp as well, and dp by dx. So what is dp by dx? Dp by dx is nothing but dp by dx. That means d dx of p. P is nothing but x0 x minus x0 divided by h. Look at this here, x0 is a constant, so this will be 0, and x, this will be dx by dx, that means 1, and h is constant, so you will find 1 by h. That means dp by dx is nothing but dp by dx is nothing but 1 by h. So you put here 1 by h. And finally you will find dy by dx, this will be 1 by h of this one. Okay, del y0 plus 2p minus 1 divided by 2 factorial del square y0 plus and so on. Okay, this is your equation. And now you can do another thing. So this is the first derivative, and as well as you can find the second derivative also. So for a specific point at x is equal to x0, if we set the limit, now if you set the limit x is equal to x0 for the initial point, p is equal to 0. Okay, for x is equal to x0, look at this equation, including this equation. If x is equal to x0 at the initial point, the very first point of your data set, x is equal to x0, so p is equal to 0. And if you put the value of p is equal to 0 in this equation, you can simplify it and found that you will found dy by dx, this will be nothing but 1 by h. This is at actually x is equal to x0 at that point. Initial point 1 by h del y0 minus half del square y0. Just eliminating the coefficient of p, you will find del cube y0 minus 1 by 4 del to the power 4 y0 plus so on. So this is your equation. And differentiating with respect to x, again if you differentiate, that means based on this equation, if you differentiate second time, d square y by dx square, and in the same manner, if you put d square y by dx square, you will find d square y by dx square, this will be 1 by h square. In a similar manner, you will find del square y0 plus p minus 1 del cube y0 plus 6 p square minus 18p plus 11 divided by 12 del to the power 4 y0 and so on. So this is the second derivative. In the same manner, you can put the third derivative and so on as your requirements in the problems. And up to which terms you will take, that means del square y or del cube y, this will be depends on your data set. That means in your difference table, if you have the coefficient up to del to the power 4 y0, so you need to go up to fourth term, that means p minus 1, p minus 2, p minus 3, and then you will solve consequently. So this is the use of Newton forward interpolation formulas for the derivation purpose. So this is one steps. So and now the question may arise: what's the use? Okay, in which cases we will use these new interpolation formulas as the derivatives, like some problems, like the suppose you have the speed versus distance versus time, that means for a rail or for a vehicle, you record a set of data, or for an experimental purpose maybe you record a set of data for a certain time respect to the distance, that means after 1 hour the train passed 50 kilometers, then next 1 hour it passed another 50 kilometers, then 60 kilometers and so on. So if you have a set of data, um, time versus time versus uh, time versus distance. Okay, distance suppose kilometer, and time maybe minute or second or hour, anything. So time versus distance, you record 5 6 or 7 set of data. So time starts from 0, after 60 minutes, after 120 minutes, after 240 minutes. Okay, and and go on. Okay. So sorry, this may be 120, then 180 equal distance, and 240, 320. So this has a set of data corresponding a distance you may found at initial time. It's in the your station, and then it goes up to suppose 40 kilometer. Then next it at when the time is 120 kilometer, it's in your distance mark. It is suppose 90 kilometer. Then again, and it may come for one 140, then distance. Okay, with the time it pass with the distance and so other data. So this is your set of data. So if I ask you what will be the velocity. You have the time versus distance data. Distance data, this is suppose x or s, anything at this a, or this is t. So if I ask you to find what is the velocity of this train at t is equal to 50 second or 60, it's 50 minute or 60 minute, anything, maybe t is equal to 50 or t is equal to 60, anyone. So what is the value of uh, velocity, what is the velocity of the train at that time? So here you have only the time versus distance data. So how will you calculate the velocity? So here is the technique and use of these types of derivations and equations. Suppose we know v is equal to, okay, or ds by dt, any notation. So change of distance with time, that's nothing but the velocity. So that means to find the velocity you need the first derivative of x. That means as time versus, if you have the time versus distance data, so from this you will find the if you take the first derivative, actually the data should be in the reverse order. Okay, data should be represented in the reverse order, that means distance versus time, so that you can find dx by dt. Okay, dy by dx, that means dy by, no sorry, it's okay. That means this is your independent variable and this is your distance is the dependent variable. So you can simply find from these knowledges, you can simply find the velocity of the first derivative. So again, if I asked what is the acceleration, that means a at that time, so this is nothing but acceleration is nothing but dv by dt. Okay, you is known in the, this is very well known in the physics, in the physics and mechanics, you know. This is again d square x by dt. Okay, the second derivative of the x with respect to dt square. Okay, so the concept is here, the first derivative and second derivative. So for certain point, suppose t is equal to 50. Okay, initial point, you know the initial point and another point, so you can simply calculate the p. Okay, x0 h is nothing but the increment, that means 0, 60, 120, 180, 240, 330. That means h is equal to, in this case the distances are 60. So if you know this, all the things are known, h is known to you.
স্যার
Okay,
স্যার এখানে কি টাইম ইন্টারভেলটা ইউনিফর্ম হবে?
If you want to use the Newton's forward interpolation, forward interpolations, that means forward difference formulas. The basic of the Newton's forward interpolation formulas is that the times are, look at this point. If you use these 3 points, that means forward interpolation, backward interpolation, and central interpolation, the h
এখানে
must
এক্সটা
be
ইন্টার
equal. Equal.
ইউনিফর্ম।
And if it's not equal, in that case you should go for the derivatives of the Newton divided difference and Lagrange interpolation formula. So all the formulas are known to you, just you need to take the decision based on your data set. If it is equal interval, then you will go for here, and if it is not, then you can go for here. Okay. And at this stage we are discussing about the derivatives of Newton's forward interpolations, so the h must be equal. So every data is known to you, and the first derivative of this dy by dx, like this is also known to you. So you know the p value, you know from the difference table you will get these the coefficients del y, del square, del cube, and go on. And you will get also the value of h. All values are known to you, and after putting all these value you will find the values of required derivatives. That means fast derivatives, that's velocity, acceleration, or anything else. So many types of engineering problems you may find in your exam, or examples of these books, like time versus distance, time versus velocity, and another one may be time versus angular velocity. Okay. And based on the mechanics or physics formulas. And a population growth rate, this is another term, the population growth rate. That means if we count the population with respect to time. After 10 years the population is this, after 20 years population increases up to this. So you have a data set with population, time versus population. So if you want to know the growth rate, in which percentage population is growing, that means I, growth rate. This is nothing but the slope of the line. That means if you plot time versus population, you will get a not like this. Population is always increasing, so you will get to this, like, so this slope is your I, population growth rate. Okay. And slope is nothing but dy by dx, or in this case dp by dt, anyone. In general case, we count the population in thousand with respect to years. Say 1951, the population is 19,000. In 1961, the population is 36,000. In 1971, it's for any city, or any else area or country, anything. So the popular calculation of growth rate, this is also very easy by using these uh, equations. And another formula, you have the Newtons. This will be for your self. Other formulas, this will be for your self study. Derivatives of Newtons backward difference formula. Okay. So Newton's backward derivatives using backward difference formula. So backward difference formula is also known to you. Y is equal to yn plus p nabla yn plus p into p plus 1 by 2 factorial yn p p plus 1 p plus 2 3 factorial yn plus dot dot. So this equation is already known to you. When you are going to solve for the Newtons for backward interpolation, this equation is already known to you. So you will simply take as before dy by dp, and then you will calculate dy by dx. This will be 1 by h yn plus 2p plus 1 by 2 factorial 3 factorial yn. Okay. And we'll go for another values. So at last point, say if you want to find the values of x is equal to x, and you will simply p is equal to At x is equal to x and p is equal to 0. For these cases, here we start from the xn, that means the end point for the backward interpolation. So, and again for the second derivatives, you will take the second differentiation d square y by dx square. Okay, so this is the notation and the use of the Newton's forward difference, backward difference, and for the central difference, we studied maybe three or four formula for central difference. For central difference, central interpolation. For the central difference interpolation, if you data in the central range, we known very common equation is the Stirling's formula. If you take the derivatives of Stirling's formula, first derivatives of Stirling formula, and then we'll find with respect to p. So actually, in if you take the derivative of Stirling's formula, it will give you a very complex function. Okay, very complex calculations. In these, up to these cases, you can find a harmony in the equation. You can easily memorize this. But Stirling formula itself a complex formula because it use the average of two coefficient. In each case, it use the average of two coefficient for the odd number and even number one coefficient and so on. So it's a complex formula, so it will be complicated for the central difference. You can preliminary you can just get the idea for the forward and backward as well. Again, for or if you try, you may try at home for the Lagrange interpolation formula. So in Lagrange interpolation formula, all the values are unequal. So there have five or six individual terms based on your data set. Suppose if you have six number of data, you will get an equation of x up to sixth order in each segment. That means if you can recall, there is a large equation in Lagrange like this. Okay, so the function in the function of Lagrange interpolation, this is a large function. So if you can take the first derivative of this function, so definitely it will be a huge task for you to find and then simplify this equation. First you need to make some simplification, then you will take dy by dx. Okay, you will take dy by dx and d square y by dx square, these things. Okay, so this is the techniques. How will you use these techniques for based on the interpolation? Now we will go for an example to show how to find the first and second derivative of a function. Before that, we can note another things, that is the maxima minima of a function. So for a tabulated function, that means you have a data table, five or six data. Definitely this data set will represent a function or represent a curve. Okay, or a line, anything. In while studying, I think in calculus, you studied how to find the maximum minima of a function. That means to find the maxima minima, first we will set the dy by dx is equal to 0. Could you remember these techniques? The maxima minima, we need to take first derivative for a function dy by dx. Put dy by and we put it dy by dx is equal to 0. That means there may be dy by dx is equal to function and this is equal to 0. Then we solve for x, you will find two value. Okay, two value of x or anything. So based on these values, we said okay, for this value, one is maxima and another one is minima, like this. And then we will go for the second derivative, and in second derivative you will find the negative value. The negative value is maxima and another one maybe minima, anything else. This is an previous concept, you already familiar with this concept. So again here you can use this maxima minima function. So for this, if you have a data with the time versus distance or time versus like this, actually if it is a time versus distance is increasing, If you have a data set like time versus velocity, suppose for a train, you starts from Chittagong station and you record the time versus velocity. Okay, you sit in the engine room, you will record the time versus velocity. So time is increasing. Okay, time is increasing, 0, 1 hour, 2 hour, 3 hour, 4 hour, hours, 5 or 6 hour is enough to reach. And velocity, at the initial velocity will be 0, and then velocity will increasing. Suppose 60 kilometer per hour, 70, 75, 73, 50, and then 0. Okay, cause a train starts from this one station and it reaches another station, so velocity must be increasing intermediate time, and while you come to close to destination, velocity is again decreasing. That means the profile, time versus velocity profile is something like time versus velocity profile is something like this. Okay, it's increase at certain time and then decrease. So for these times, here is obviously there is one point where the velocity is maximum. Okay, this may be here or maybe here, any point, maybe it's in between. Okay, so for such types of problems, you will also use these. You have this set of data, so you will use the interpolation formula to form this equation, then take the first derivative for the maximum point, and with respect to time, you will find one point in which point, at which time the velocity was maximum. You can simply calculate. Okay, it's just for or not for the application purpose. We will not go for such deep application. Simply we will learn how to find dy by dx and d square by dx square. So at this class, we will close with an example. I will show only one example, and many problems and examples of such problems you will find in books as well as previous exam questions or anywhere. The procedure is all same for all types. Let's start an numerical example. The population of a city, the population of a city is obtained. Okay, if you have the population of a city, suppose for year versus population data. See, year is your 1951, 1961. This is an actual workout example of books. 1971, 81, and 1991. The populations are represented in thousand. Okay, so this is 19.96 thousand, 36.65, 58.81, 77.21, and 94.61. So this is your data set. Okay, now you are asked to find the rate of growth in 1981. Okay, in this point, what's your population growth? So which technique you will apply, or which equation you will apply? First of all, look at your data set. Here year versus population, so obviously this is your x independent variable, and population varies with time, so this is y dependent variable. So look at this year 1951, 1961. That means in this case h is equal to 10. Okay, this is clear. Equal interval, the space are equal spaced x data. and you are asked to find the population at 1981. So this is your x0, or this is your y0, y1, y2, y3, y4, or yn. So your point is very close to int of the data set. So you will use Newton's a backward difference formula, and you will take the derivative, first derivative of the backward difference, as because you are asked to find the rate of population growth. That means rate of population growth, this is nothing but dy by dx. Okay, and you need to find the value of dy by dx at which point x is equal to 1981. Okay, so the first task is to form the difference table. Okay, this is the common thing. You first need to form the difference table. The difference table will be, sorry, it's not responding. Okay, x, this is your year, y, this is population. Okay, and populations are corresponding 19 point, look at this, 19.96, 36.65, 58.81, 2161. Okay, so first derivative, as we use the backward interpolation, so first derivative is nabla y, this is 6922.16, 18.40, 17.40. The second derivative, this will be 5.47 minus 3.76 minus 1. This is the, as from your previous problems, as equal 9.23, 2.76 for y, you will find 11.96. So in Newton backward interpolation formula, which values we picked, if you can remember, backward, for backward interpolation these values are required. So you get already the required coefficients, and look at this, you have del to the power nabla to the power 4y. That means you need to expand the equation while deriving, taking the derivatives. You need to expand your equation up to this. That means these are actually n. Okay, up to this point. So we know that the first derivative of that equation of Newton's backward interpolation equations, the first derivative at x is equal to xn, this equation is actually 1 by h yn plus 2p plus 1 divided by 2 After simplification, I am writing the equation after simplification. Plus 3p square plus 6p plus 2 divided by 6 cube yn plus 2p cube plus 9p square plus 11p plus 3 divided by 12 to the power 4y0 plus dot dot dot. Okay, so this is your equation. And now for x is equal to 1981, what is the p value? P is equal to, we know, x minus xn divided by h. Here x is equal to 1981 minus xn. Xn means last terms, that means 1991 divided by h is 10, that means it is 9 minus 1. Okay, p is minus 1. So you can put this value here, two unknown h, p and coefficients. So dy by dx at x is equal to 1981, this is nothing but 1 by 10 nabla y, that means these terms 17.4 plus 2p, that means 2 into minus 1 plus 1 divided by 2 multiplied by this term, that means minus 1 plus next one 3p square plus 6p, p means minus 1 plus 2 divided by 6 multiplied by this one, that means 2.76, 2.76 plus the last terms, and all the values are known, so you will get the uh, last terms. After calculating and simplification, you will find the value is 1.6440833 dy by dx. X is equal to 1981. So your population growth rate at 1981, this is 1 point. Okay, that means 1.64%. This is your population growth rate. So here is the simplified example, and you will find similar many example for functions for given values. So you are asked to find first derivative or second derivative, or sometimes you may ask to find such types of problems. Say you have the population versus time versus population data. You are asked to find the growth rate. So in that case, you must need to know whether the population growth rate is the first derivative or second derivative. You need to know whether the velocity is the first derivative or second derivative of the time function, time versus distance function, and the angular velocity, omega, angular acceleration, that means omega. So this is the first derivative or second derivative of angular displacement. Okay, these are the previous knowledge of science. So this we will hopefully know that these are the known to all of you, so no need for further explanation. And you need to catch the problem correctly, and then you will choose the suitable path. That means your data set is the initial portion or the ending of your data sets, and which parameters are asked to find. And then based on all these decisions, you need to go, okay, I will use the first derivative of backward. And in the specific these problems, if I asked you to find the population growth rate at 19, suppose 1955. Okay, at 1955, what is your population growth rate? So if the problem is not 1981, it's simply 1955. So for 1955, what you need to do, dy by dx at 1955. So look at this 1955. This is your initial the initial portion of your data set, something like here. So you need to go for the difference table is equal as well. That's the symbols of changes. That means this will be del y, del square y, del cube y, and del 4y. That means first difference, second difference, these are the same, and you need to choose at previous cases we take the equations for Newton's backward interpolation, and this case for x is equal to 1955, for the year of 1955 we need to choose the Newton's forward interpolation, first derivative of Newton forward interpolation formulas, and for that case you need to take the coefficients like this. These coefficients are required. Okay, upper diagonal. So these decisions should make by you which equation you will take, and then take the first derivative of this equation, first derivative of Newton's forward interpolation. We already find this. This is the first derivative of Newton's forward, this formula. This is the first derivative. So you simply put all this value, you will calculate, you need to calculate the p value in the forward difference. P is equal to x minus x0 divided by h. So you will calculate the p value as well as use these values and the coefficients, then you will find the required growth rate. Okay, so I think this is the ending of Newton's numerical differentiation. At next class, hopefully, we will start the numerical integration. Okay. So, if anyone have any question, the floor is now open. You may ask any question, if any, or either the other that I
হ্যালো
will.
স্যার
Hmm.
স্যার ইন্টারপোলেশনের কয়েকটা এক্সারসাইজে দেখছিলাম যে মিসিং ভ্যালু বাইর করার জন্য মানে ম্যাথ দেওয়া হয়েছে, ওগুলা কি স্যার প্র্যাকটিস করতে হবে?
Interpolation.
জি স্যার।
Yes. The main task of interpolation is to find the missing values. Okay.
মানে স্যার যে টেবিলটা দেওয়া ছিল এখানে এক্স এর ভ্যালুগুলা দেওয়া ছিল না।